Welcome everyone to this webinar on the seismic performance and retrofit of light timber frame buildings. So I'll just introduce our speakers. So we have Catalina Miranda as a structural engineer from Chile and a lecturer at the Joint Center for Disaster Research at Massey University. Across a career spanning both industry and academia, she has led and delivered impactful outcomes in earthquake engineering. Her research sits at the intersection of structural engineering and social science, with a particular focus on seismic risk communication and on reducing risk and improving the resilience of timber-framed housing. We also have Angela Liu presenting as well. Angela obtained her PhD in structural engineering from the University of Canterbury and is currently a senior structural engineer at BRANZ. Prior to BRANZ, Angela worked at a New Zealand structural engineering consultancy for 10 years. Angela's research interests include seismic performance and retrofit of buildings and resilience of light timber framed houses. So Catalina, feel free to share your screen and begin your presentation. Thank you very much.
Cool. Thanks for that. I hope the sharing is working. Hi, everyone. Thanks for coming to our seminar today. So I'm going to be presenting first, and then Angela is going to present. So yeah, I'm Catalina. Tom introduced me, and my presentation today is going to be an overview of what I've done or what I've been doing for the last few years with regard to existing residential timber frame housing. Next, maybe takes a minute. So everything started, this research started a couple of years ago when I collected data on timber frame houses in Wellington. I particularly focused on this study on houses located on a slope. I surveyed around 80 houses in Wellington with a mix of houses located on different sort of slopes. When I collected this information, I went into different houses and I surveyed houses for about an hour, and I looked at the foundations and the subfloors. I recorded the roof type, the plan shapes. I draw plan shapes, and I look at the connections where it was possible, of course. And these are just some examples of what I have collected. So considering this information, the information we collected, we developed a typology, specifically looking at houses located on a slope. So the typology also included information about the type of floor. For example, the majority of houses were sitting on timber piles. And we also collected data where we found that walls at the subfloor level were mainly the ones at the perimeter were mainly weatherboards. So you can see the typology and some findings here. This is just a summary, by the way. So we developed this typology to decide how to build numerical models or to define a geometry of those numerical models. So for simplicity, as a first approach of numerical models of existing houses, existing timber frame houses in, I should say New Zealand, or that I'm aware of, we decided to model just the model number one, the one you can see here. It's the simplest, but maybe not the easiest. I'll get to that in a minute. So when we model the houses, we consider model one, and we vary the dimension of the model one, so vary the length across and up down slope, and we also vary the height of the foundation on the down slope side, and we also vary the distribution of external walls on the first floor. So we ended up with 81 different numerical models, and we considered a linearity of the model and on the subfloor area. To be honest, it was mainly because we didn't have the data for calibrating the upper story existing walls. So that's information that we're building on. And also we wanted to focus on the subfloor area because that was the area that we wanted to implement some retrofitting, and we have data to run the models after retrofitting. And also people have indicated that is the area that is the easiest access to. So it's easier for homeowners to access the subfloor area and do some retrofit in that area instead of, be changing all the walls in the upper story or the roof. So we calibrated this model using data provided by BRANZ. It included information of the subfloor performance of with and without retrofits. The retrofit that were considered was adding a ply on the wall on the downside of the slope, as you can see in the picture, and also connecting concrete piles using infill concrete. Just as a summary, when I click here, yes. As a summary, we conducted some studies. I'm going to just show a few of them to analyze the vulnerability of houses with and without retrofit, or how some geometric parameters influence the performance. For example, here you can see that the plant shape relative to the slope was analyzed against the drift and torsion. So we can see that houses with a similar plant shape perform differently depending on the slope orientation. Here is the data for a 500-year return period, where we can see that houses with the longest side on the up-down slope direction perform worse than houses with the longest side across the slope. And oh no, was too fast. So then we compare houses with and without retrofit using fragility curves presented using fragility curve for multiple strip analysis. So we consider the average drift that we measure at different areas of the different point of the house, the subfloor and the floor level. And here I'm just showing the probability of exceeding 1 and 3% of drift, because it's what we see usually in houses when we can observe some level of damage. It might be too small to see here, but happy to share this later. But basically, what we can observe from this data is that houses after retrofit showed an improved performance, which is kind of like what we expected, obviously. But going back to the parametric study, we also found that this sort of strengthening, the one that we use, will be more effective depending on, for example, the plant shape relative to the slope. So that's kind of interesting, because we might be offering retrofits and they might be more or less effective depending on the house that you're applying the retrofits to. And as I said, this study was conducted in Wellington. And one of the questions we had from some reviewers that reviewed the papers was whether we can extrapolate these findings across New Zealand. And we said, well, maybe depending on where in New Zealand. So to try to understand if we can extrapolate the findings, we have conducted some surveys in Auckland and in Christchurch, but it's definitely more to be done. So we can develop further typologies to understand the different variety of existing houses across New Zealand, and then of course to model houses, because that's what we like to do in engineering, right? So since we went to Auckland, we came to Auckland because I'm in Auckland today. We also wondered if we should include some flooding analysis. I know this is slightly different from earthquakes. Just to try to understand the vulnerability of timber frame houses in flooding events, and if we want to retrofit them, which is mostly lift, then what benefits or not benefits from a seismic perspective will that provide? So this is a project that is happening at the moment, so not many results yet, but it's just going to explain an overview of the project. And back when I was modeling houses in Wellington, one of the challenges I faced, it was the lack of data in existing housing. So we're doing a couple of things to kind of like develop further the models of existing houses in New Zealand. So I did a couple of interviews with engineers, where they have indicated that this is the most typical connection that they used to connect the piles and the barriers when the houses are lifted. So we done testing at UC to understand the shear capacity of that connection. Here is like flip 90 degrees. So that's what is in that direction just for facilitate testing. And then we also currently doing some testing at BRANZ that it hasn't finished yet, just to understand more like the system performance when we have the bear you can see here in the picture. And so we are varying the different height of with different varying the height of the pile and using the same connection. So that's going to be data that is going to help us to then model the subfloor of the house. And then, of course, we need to include the upper stories, but we'll get there. And since we were talking about flooding, this is kind of interesting. We also done the testing of this connection using after soaking the connections in water for a different period of time. And then we tested the connection straight after being wet, just to get the shear capacity. And also we tested the connections after they went back to dry conditions. We soaked these connections for 3 days, 1 day, and half a day. It was quite an interesting thing to do. Still analyzing the data. I was actually working on that yesterday, and we can see some difference in the strength and the final and in the stiffness, how it changes depending on the time that it's being underwater. So that is pretty interesting. And also the mold failure of the nails. They mostly withdraw, but interestingly, when we tested the connections after they went back to dry conditions, we have the nails withdraw, but also got split into two. So that was interesting to see as well. Just a bit of an overview of other aligned projects that I'm involved is that to extend and to keep understanding the performance of the behavior of suspended timber floors. We're also going to be doing a 3D setup, not 3D test, 3D setup of a suspended timber floor at BRANZ. And we're going to be it's still a lot to define on this project because it's actually start next week and officially, and we're going to probably be using 2 actuators to kind of like push or maybe shake the subfloor. And then another project that is coming up, if you want to know more about it, maybe we can talk about that later, is that we're planning to conduct a full-scale testing of an existing timber house in Auckland, the ones that are being affected by flooding after the last flooding events. So more to come. And that's me. Thank you.
I'm Angela. I'm a structural engineer at BRANZ. My presentation today is seismic resilience of light timber framed residential houses. And we are going to talk about the research initiatives behind the current research focus areas. And I'm going to talk about the current BRANZ project in relation to the residential houses. And I will talk about what we have done, the progresses, and intended research outcomes. And let's look at the research initiatives. Currently, we have quite a few research focus in residential areas. All those research focus actually was really shaped by the damage evidence in Canterbury earthquakes. During Canterbury earthquakes, the emergency state, BRANZ actually was in charge of the suburb operation, looking at checking the safety of the houses to be occupied. And so we visited lots of houses. Subsequently, after the emergency state was lifted, we did the more detailed house damage survey for about 55 houses. And this exercise actually during these exercises, we found all the light timber framed houses, low rise, they all achieved life safety. However, the damage was significant. And especially, we actually see the highlighted vulnerable area. It's just those two categories, the houses with hybrid bracing systems, or houses, or whole side houses. Like this left side of this picture is like, it's a typical hybrid bracing system, and got steel portal frames. Rest of those bracing systems are light timber framed walls. This type of houses didn't perform well in Canterbury earthquakes. And the right side, those two pictures actually show the red sticked whole side houses. So that's earthquake damage evidence, which helps shape our research focus areas. And so we have 3 research focus areas. The first one is damage controlled design of light timber framed houses. Clearly, the life safety is no longer a relevant target, so we aim for damage controlled design of residential houses. Second focus is seismic resilience of timber houses with hybrid bracing systems. And third one is whole side houses. That's our research focus area. And the first one, damage controlled design of residential houses. In this focus area, we actually did quite a bit of work. First component of work is we examined bracing design basis of 3604 housing design standard. We actually did lots of data mining of available P21 testing data at BRANZ. We have so many data, so we actually analyze those data. So this work actually led to those findings, ductility deformation capacity of plasterboard wool. We found actually it's not so high like what 3604 has assumed. Actually, we think it's probably a ductility 2 or even less than that should be more appropriate. And we also, through this exercise, we found a specifically designed bracing system in residential houses need to be compatible with proprietary timber framed walls. And the timber walls we found with if the lining are wood based like plywood, they are more ductile than plasterboard walls. So this piece of work also enable us to develop a plasterboard wall hysteresis model. We actually have some sort of publication already put out there for people to use. That's one component of damage control design work. We continue to look at what else we have done. We did ceiling diaphragm testing. We did the full-scale wall to floor test. At both of those tests, actually, one aim is try to establish the in-plan rigidity of ceiling diaphragm and floor diaphragm. Also try to establish the relative stiffness or just rigidity of wall and floor or ceiling diaphragms. This will help us to do the numerical modeling. And from this experimental study, what we did is we developed a damage state quantification methodology. This quantification methodology actually allows for the damage, meanwhile allow for the repair actions. So we also developed wall at the ceiling diaphragm or floor diaphragm hysteresis models. So for us to do numerical modeling. So we actually published some of our testing data or models in those publications. So that's another component of work in relation to damage control design. And we did more work in this focus area. We actually tested walls on suspended timber floors because the P21 test never really investigate the effect of wall base condition or the bracing performance of walls. And so we did this. It's just to build a suspended timber floor. We actually had the plasterboard wall on top of a suspended timber floor. From this experimental work, we found base condition of the wall actually significantly influence the wall performance. We found actually light timber framed wall or suspended timber floors have a significantly lower strength and stiffness compared with P21 test setup. We also found the failure mode is quite different for when you compare plasterboard wall or suspended timber floor with the plasterboard wall or just like P21 setup. So we actually have the research findings published in just 2024, and let's continue to look at what else we did for damage control design. We actually based on the development models for walls at the ceiling diaphragm, floor diaphragm. We did quite a bit of numerical modeling. And we did a nonlinear pushover, use ETAP. We did a nonlinear time history analysis, use just the software developed by Minho. And what we actually, especially we focused on just checking the current irregularity limit. Both those sort of analysis found the current irregularity limit of 3604, it's too linear. It's just eventually very irregular houses designed according to 3604 will suffer significant damage. So we have two actually journal papers published in relation to this topic. So I think I have to mention this project, damage control design work. We're working with UC, Max PhD project. Actually, quite a few of you guys, actually, Cadbury people working, on this project. BRANZ actually involved in this project. It's a great opportunity to further advance our understanding for the large timber framed houses. So that's the damage control design work. And the next research focus area is hybrid large timber framed houses. This focus area is built all the foundation work in damage control design, that research area. So in damage control design, that research focus area, we identified why the inclusion of hybrid bracing system exacerbate the earthquake damage in residential houses. So we identified the root cause. Then we developed solutions for specifically designed bracing system in residential houses. We actually, with collaborator, especially engineer in New Zealand, we produced the guideline for professional engineer and BCA to use, such as the publication like steel portal frames in residential buildings. It's just like that provides some sort of guidance to enable consistent design of those specifically designed bracing system. Also, help contributing to the, consistent approach in issue the building consent. More work is going to do in this area. We try to basically that produce engineering data set for a common bracing system. So engineer can use those sort of data in their design. We also try to develop a guideline for bracing designs of hybrid large timber frame houses. We are thinking about developing design examples, hybrid residential houses. So that's a hybrid system, one component of work. And next focus area is whole side light timber framed houses. We actually in this area, we work a lot with Wellington City Council, UC, Massey University, and Earth Science of New Zealand. And currently, this area, like a BRANZ component of work, is we categorize the common practice. We actually did somewhat similar to what Catalina did, but we did a little bit differently. We actually reviewed the literature, and we, based on the common practice, we categorize engineering characteristics, not only based on literature and also based on the, evidence through the housing survey. We actually identified seismic vulnerabilities in whole side houses. This identification is mainly through the desktop study. And recently, actually, with the help of Wellington City Council, we surveyed whole side houses. This survey will help us to, inform our testing, design, and numerical modelings. And we also have done some sort of testing. We tested the subfloor bracing system commonly used in residential houses. And next component of the work is
Angela, you've got 5 minutes left.
Yeah. We actually let's talk about engineering characteristics. After we review the past historical housing construction guideline and standard, what we found is we can actually classify or categorize the engineering properties of whole side houses into 3 categories. We find whole side houses mainly 3 categories. One is built into ground. It's like this very left picture. It's just like so many retaining structure. It's just stepped, cut into the hole, build the houses just into the ground. And second category is the whole side houses are braced at different level, like this middle picture. Actually braced at this top level, like where my mouse is, and braced at this level, so many different levels. And the third category is the main structure of whole side houses are braced at the same level, but the bracing system are mixed system, like this very right pictures. Actually, the main structure is braced at this level, but the subfloor foundation, it's like a timber system, braced pile, anchor pile, and a concrete system. So that's the engineering characteristics classification. And the testing we did, we actually did subfloor bracing system testing. The lab testing, it's like this, just recently completed. We actually tested the subfloor braced pile systems. And actually in the past, BRANZ did some sort of field testing of braced piles, anchor piles. So we are actually mining those data, try to develop the models for us to do numerical modeling. That's experimental work. Let's look at, we have, published a couple of papers in whole side housing area. and more work in this area. We are going to do more testing, and we are going to do more numerical study for whole site houses. We also ultimately we want to develop retrofit solutions at guidelines. So actually, in detail, the retrofit, the intended outcome is we try to develop diagrams, sketches for improving whole site housing performance. We also want to produce engineering data set of subfloor bracing systems, and hopefully we will be able to develop design examples for engineering professionals to use. Yeah. And other issues I want to mention is we are working on a few things like we try to think about what's the implication of this TS 1170.5 or whole site housing construction, especially for Wellington. We try to consider the soil foundation interaction. And we are working currently with on landsliding, just to touch a little bit, landsliding and flooding effect on whole site houses. We're working with earth science and UC at Massey University in this area. And BRANZ also have a project, effect of flooding or condition of houses. So we work collaboratively internally and externally. And yeah, what I said is like it's quite a complicated area. We need to work together with you guys and to deliver better, useful output. So that's us. Thank you.
Yeah, great. Thanks. Thank you very much, Catalina and Angela, for great presentations.